Hi everyone, and welcome to this video where I'll be showing you how to optimize your scene with the help of the Performance tab. It's not always clear what's slowing a scene down, especially when working with large, complex scenes. So this tab can help you identify what nodes are most expensive in terms of CPU time, with the help of a heat map in the node graph. This can allow you to make more informed optimizations in the node graph in order to speed up the processing time and get your renders started much more quickly. Inside the Performance tab, you'll be provided with some information about your scene. So you'll be able to see the total number of nodes in the project, as well as the number of contributing nodes and the number of selected nodes. This information is really helpful, especially, as I said, when working with larger scenes, as it's really easy to lose track of how many nodes are in the scene. Now, these numbers include any nodes contained inside groups or network material crate or edit spaces, and this includes nodes such as the Gaffer 3 or group stacks, because they're super tools and are made up of groups of other nodes. The selected nodes displays two numbers, so the first is the number of nodes that you have visibly selected, and the number inside the brackets is the number of nodes contained within, which may not be visible from the root level node graph. The number of contributing nodes indicates how many nodes contribute to the viewed node. Depending on how your scene is set up, this could be much fewer than the total number of nodes in the scene, because graph state variables will have an impact on which nodes are being used at any one time. To illustrate this a little better, you can enable the dim nodes not contributing to a viewed node under the view menu in the node graph. And this will show much more clearly which nodes are not contributing, as they'll be dimmed and their custom colors will be disabled. For example, in this project, I have different render nodes set up for different render layers, so only one of them is being viewed. I also have a variable switch set up for the lighting overrides, so the chosen shot will determine which nodes contribute to the viewed node, as I'm making overrides on camera angle and shot levels. So let's set off a preview render with profiling now, so we can start taking a look at which nodes may be slowing us down. So once the render starts, we can see some more information in the Performance tab. When Auto Load Latest is checked, the results from the latest profile render, which is a JSON file, will be input here. It's worth noting that you can also browse and select a different file if you want to visualize the results from a previous render. This is also really helpful if you want to share this project with other artists, as they won't even need to set off a render. They can just input the JSON file that you shared here. I'll come back to the heat map in a moment, but first let's take a look at these times. So we can see the elapsed time, which is the time taken from setting off the profile render to it starting, the CPU time, which is the total processing time added up, and the op count, which is the number of contributing ops. So this number may be different from the contributing node count, because sometimes nodes contain multiple ops, and sometimes not all ops are related to a node. In this table, we can also see the CPU times listed from most to least for the most expensive nodes. The no name entry represents non-node related ops, such as implicit resolvers. As a side note, you can view the implicit and any custom resolvers by toggling the icon and clicking implicit resolvers active in the scene graph. From the other entries in this table, we can get an idea of the most expensive nodes and see how much processing time they took. So from this information alone, we can start to see what nodes are taking the most time. But we also have an option to show a heat map. So when this is enabled, the processing time for each node is represented with colors in the node graph. So now we have a really nice, clear visual representation of how expensive each node is. You may also have noticed that when the heat map is enabled, any custom node and backdrop colors will temporarily be disabled to make the node colors even clearer. By default, the red nodes are the most expensive and the green are the least expensive. And you'll have a gradient of colors in between the two. This color scheme can be changed, and I'll demonstrate this a little bit later in the video. So in this case, we aren't getting too much of a gradient just yet between the red and the green, because there's such a big difference in processing time between some of these nodes, and the colors are calculated relatively. as you can see from the QuickTime key in the node graph. So we can see the 3 most expensive nodes are taking between 5 and about 15 seconds, and then the rest are all under 1 or 2 seconds. And the total elapsed time is about 23 seconds. So this gives us a good indication of what to look into first. The USD in nodes bringing in the character animation are some of the heaviest in the scene. Now, geometry imports will always likely be fairly heavy, but in this case, they've been exported as USDA files, which is unnecessary for character animation. So by converting these to USD, which can be done quite easily from the command line, we can drastically reduce the size of the files and therefore reduce processing time. I've already converted these to USD, so I'll swap them over now. By using the information in the Performance tab, it was really quick to identify these heavy asset files, which may have been exported by mistake in the wrong format. So I'll start another render to see what difference this has made. And you can see just by doing that the processing times for those heavy nodes has been hugely reduced. So the total time is now just over 1 second as opposed to 23 seconds, and all the nodes now take less than 1 second. With that change, we can also see much more variation in colors within the node graph as well. If you find it difficult to distinguish between the more subtle color differences, then the color scheme can be changed under View, Heat Color Map. So you can set this to the theme of your choice. Some themes may make it easier to see the color differences of some nodes. For example, with this one, we can start to see some of those more subtle differences. And so now we can continue to optimize. I can see that the asset imports are still some of the most expensive nodes, but there's not much else we can do to change that. And as I said, geometry imports are always likely to be relatively heavy. So instead, we can look at some other ways of optimizing. If you aren't sure what to look for when optimizing, there's a really useful section in the dev guide under Performance and Optimization for designing node graphs for optimal performance. This outlines some of the ways that your node graph can be slowed down and how to organize it to speed things up. The first section talks about the importance of pruning as early in the node graph as possible to avoid processing any unnecessary locations. And then it covers how to structure nodes to take advantage of parallelism in both the scene graph and Octree to speed up your scene's processing times. So let's jump back into our project and have a look at what changes we can make. Apart from the asset imports, this cleanup group looks like it could be slowing things down. This contains a prune node, so I'm going to move this entire group as far up as possible to just underneath the geometry imports, but before any transformations. This means that any cell statements that are searching the scene graph within any of the transform nodes will have less locations to search, as some geometry has been pruned first. And just looking back at the stats from the previous render, I can see that the op count is much higher than the number of contributing nodes. This could suggest that some nodes are being processed twice unnecessarily, so let's have another look in the node graph and see if there's anything that we can change. So down here we have an animation retime, which is isolating and retiming the animation for one character before merging it back with the rest of the scene. This looks like the cause of the op count being so high because everything above this section is being processed twice. So I'm going to move this section up as well, and this can sit anywhere under the character geometry. So I'll put it here and I'll set off another render with profiling so we can compare the times again. And as you can see, this is a little quicker again, but more importantly, the op count is lower, so we can be sure that no ops are being processed more than once, unnecessarily. Bear in mind that this is a relatively light scene, so any changes are fairly small in terms of the elapsed time, but when working with larger and more complex projects, there'll be huge differences and you will really notice the benefits from understanding the ways that you can optimize your node graph. And this optimization process is made even easier with the help of the Performance tab. Thank you for watching. I hope this video was helpful. You can refer to the dev guide for more information about optimization, or refer to the user guide for documentation on the Performance tab and any other features of Katana 6.